In earlier episodes, we saw classification of minerals, and we shall continue from there and discussing today rock forming minerals, especially silicates, and to less extent oxides and sulphides. A very early estimate by Clark and Washington suggested that the upper 13 km of the Earth's crust has the following proportion of rocks: 95% igneous and metamorphic, 4% shale, 0.075 sandstone, and 0.025 limestone. Present estimates may be somewhat different. These rocks are composed of different minerals. There may be over 3,000 known species of minerals. However, around 450 mineral species may be somewhat common, but a smaller group is dominant in the rocks that constitute the Earth's crust. Our theme for this lecture is that dominant group of minerals that are essential to justify its name. Not more than 30 minerals and fewer families will come under this category. Significance of these minerals for a firm grasp of petrology is essential. Opinion might differ somewhat between earth scientists as to which minerals should be called rock forming. Encyclopedia Britannica defines a rock forming mineral as any mineral that forms igneous, sedimentary, or metamorphic rocks, and that typically or solely forms as an intimate part of rock forming processes. In contrast are those minerals that have a limited mode of occurrence or are formed by more unusual processes, such as the ores of metals, vein minerals, and cavity fillings. Many mineralogists consider only essential minerals of rocks as rock forming minerals. That dictates its nomenclature and rock genesis. As per this, quartz, feldspars, and micas will be rock forming, but not clays and apatite, since clay is of secondary origin and apatite an accessory. Many would not include secondary minerals as rock forming minerals, as they were formed at a later stage than the original and obliterated its primary character. We will have to take a middle position in this respect. We would consider rock forming minerals as those making up the bulk of all the rocks that constitute the Earth's crust. Thus, pyroxene, plagioclase, and iron oxide minerals will be called rock forming minerals in a basalt. Calcite or dolomite would be rock forming for limestone, dolomite, even though they are non-silicate and of secondary origin. Similarly, quartz will be considered a rock forming mineral in rock quartzite, which is of metamorphic origin. Many of the rocks minerals in igneous and metamorphic rocks will be common to both the groups. For example, minerals in a granite will also appear in gneisses and granulites. There might be differences in the type and proportion of these in these two categories of rocks. Thus, in summary, we might then say that rock forming minerals are those handful of minerals that are very abundant and occur in a great majority of rocks that constitute the crust. Talking of igneous, metamorphic, their number at your stage will be hardly more than 8 to 12. With your increasing knowledge, you may extend them around 30, not more. These are the minerals which will decide the bulk chemistry of the rock and its nomenclature. Rock forming minerals in charnockite, a variety of granite under the microscope, is presented there. The name silicate minerals is indeed synonymous with rock forming minerals, as with few exceptions, igneous rocks are composed almost entirely of silicates, and as we know, 95% of the earth crust is represented by igneous and or metamorphic rocks. Few families dominate the common silicate minerals, including olivine, pyroxene, amphiboles, micas, feldspars, clay minerals and quartz, which of course is an oxide but generally goes along with the silicates. Now of late, we also know that rock crusts of other planets and moon are also silicates and oxides too. Thus, understanding silicates is the fundamental to our understanding of the subjects of mineralogy and petrology, and even the theme of geoplanetology. The fundamental unit of this versatile group is SiO4 tetrahedra, where Si is at the center and is linked to 4 oxygens at the corner of a tetrahedra. This linkage is considered to be 50% ionic and 50% covalent in nature. In practical terms, this makes the structure of silicates and hence the Earth's crust very strong and stable. Earlier silicates were classified on the basis of hypothetical oxyacids of silicon, meta and orthosilicates, but are now classified according to the modern concept of crystal structure arising due to sharing of 1, 2, 3 or all the 4 oxygens ions with its neighbor and the possibility of aluminum replacing silicon. This creates an unusual diversity of structural configuration of silicate structures arising from various ways in which silicon oxygen tetrahedral units are related to each other. Thus, we have a number of types of silicate structure called nesosilicates, sorosilicates, cyclosilicates, inosilicates, single chain, inosilicate double chain, phyllosilicates and tectosilicates. Apart from SiNO and Al, other important cations like iron, magnesium, calcium, sodium, potassium, phosphorus, titanium and even some trace elements whose concentration is less than 0.1% become the part of these shared SiO4 units by substitution, so long as geometrical coordination and electrical neutrality principle are satisfied. The sequence in which the silicate minerals appear from a primary magma is best explained by the celebrated Bowen's reaction series elucidated by famous experimental petrologist N.L. Bowen in the early 1900s. Through his studies of silicate melts of simple 2 and 3 component phase diagrams, he suggested that common silicate minerals that crystallize out of basaltic magma could be divided into series called continuous and discontinuous reaction series. In the discontinuous series, olivine is the first silicate to appear as small crystals belonging to orthorhombic system, typically olive green in color, vitreous, granular when massive. Magnesium variety is fosterite while phyllite is iron silicate. It is the important constituent of ultrabasic rocks like dunite, peridotite and commonly found in gabbros and basalts, occasionally in magnesium-rich marbles also. Pyroxenes, the next family, is a large one with many types and subtypes are single chain structures crystallized in orthorhombic and monoclinic systems. Augite is the typical representative, short prismatic, hardness 5 to 6, gravity 3.2 to 3.4, has two important prismatic cleavages on the 8-sided basal section with cleavages intersecting nearly at 90 degrees. Other members are anstatite, hypersthene and more than one alkali pyroxene. Ultrabasic pyroxene in peridotite and basic intermediate rocks and gabbros and basalts, dolerite, andesites are the home to this group. Amphiboles, the next group, are double chain structures with hornblende as the typical mineral, occurring as long prismatic crystals, and the two prismatic cleavages and fibrous or acicular, their cleavages intersecting at nearly 120 degrees on the basal 6-sided face. Amphiboles are characterized by hydroxyl ion and chemically are complex hydrated silicates of Mg, Fe, Ca, Al, ferric iron and sodium. Other members include cummingtonite, grunierite, tremolite, actinolite and the alkali group. These are more typical of metamorphic rocks like gneisses, schists and amphibolites. Tremolite is essentially found in metamorphosed limestones and actinolite in metamorphosed ultrabasic or basic igneous rocks. Biotite, also called iron or black mica, muscovite called white or potash mica, lepidolite, lithium mica and phlogopite, magnesium mica are the important members of the mica group with sheet structure. Like amphiboles, these also contain the hydroxyl group. These are most easily identifiable minerals due to their near transparency, foliated habit and shining luster. Schists and gneisses, pegmatites and other acid igneous rocks are the storehouses for muscovite and biotite. Phlogopite is restricted to magnesium-rich rocks like kimberlite. Lepidolite is found in pegmatites. Feldspars, the most important rock-forming minerals of the crust, dictate classification of rocks. These are framework aluminosilicates of sodium, potassium, calcium and less commonly barium. Most common feldspars form solid solutions of three end members components of anorthite, albite and potassium feldspar. Albite-anorthite combination constitutes the most famous plagioclase series, the best example of solid solution and isomorphism. Albite orthoclase or microcline combination is termed alkali feldspars. Plagioclase feldspars constitute the famous continuous series of bovine as shown in the slide. All the feldspars are of light shade. Orthoclase is flesh colored, grey or white. So could be microcline, but the most recognizable variety of this mineral is the bright green color known as Amazon stone. Plagioclase feldspars, albite, oligoclase, andesine, labradorite, biotonite and anorthite exhibit a range of composition. Pure anorthite when Ab content is 0 and An is 100 or simply An 100 as it is called, and albite becomes An 0, labradorite will be An 50, Ab 50 and so on. All feldspars are vitreous with prismatic cleavage, hardness 6, gravity 2.56. Twinning is the most characteristic property of feldspars, simple in orthoclase, repeated or lamellar in plagioclases and cross-hatched in microcline. Perthites and antiperthites are characteristic intergrowth structures in feldspars due to unmixing of two components at lower temperature. When seen under microscope, only these are called microperthites. In some undersaturated rocks like syenites, Feldspathoids, namely nepheline and leucites, will be considered rock-forming minerals. Mineralogy of the metamorphic rocks, namely schists, gneisses, granulites and marble, can be extremely diverse, since any kind of earlier rock can be subjected to metamorphic process, which takes place over a wide range of temperature and pressure. Yet, the list of commonest metamorphic minerals is not very large, as a large number of them have a wide stability field. We can divide metamorphic minerals into two groups. One, those are exclusively metamorphic mineral or nearly so, and those which also occur in igneous rocks. Common among the exclusive lists are the garnets, one of the most typical metamorphic minerals and easy to identify due to its cubic symmetry and forms. Grossularite, pink, olive green or yellow in color and is typical contact and regionally metamorphosed of impure limestone. Brownish red spessartite, that is manganese garnet, is found in metamorphosed amine-rich sediments. Deep red colored and most common almandine is commonly found in medium grade pyritics metamorphic rocks. Deep crimson pyrope occurs in high grade Mg rich metamorphic rocks, while calcium aluminum garnet andradite is found in metasomatically altered limestone skarns. Emerald green uvarovite is found in chromium rich serpentinites. Aluminosilicates too are characteristic of metamorphosed alumina rich sedimentary rocks. Kyanite, sillimanite and andalusite exhibit the best example of polymorphism. Triclinic kyanite is typically bladed in shades of blue, off-white and with dual hardness of 7 across and 3.5 along the blade, and occurs in regionally metamorphosed pelagic rocks. Sillimanite in prismatic or fibrous masses in shades of grey, green, brown with vitreous luster with a hardness of 6 to 7 and gravity of 3.3, occurring in high-grade pelagic metamorphosed rocks like schists, gneisses. Andalusite is a typically low-grade argillaceous metamorphic mineral, orthorhombic in shades of white, pink and greys, hardness 7.5 but less when coated with mica. Their main use is as refractory minerals. Sterolite, the commonly twinned orthorhombic mineral, occurs in shades of reddish brown, brownish black or yellowish brown, having subvitreous to resinous luster. It is hard when fresh, that is 7.5 with 3.5 to 3.7 specific gravity. Occurs in metamorphosed iron-rich sediments. Among the green minerals, chlorite, serpentine and epidote, even actinolite and hornblende are mostly, which are hydrated silicates, are typical of metamorphosed mafic and ultramafic rocks and are characteristic features of green stone belts of the world, which are home to gold occurrences. Jadeite, a pyroxene, is a typical metamorphic mineral, not so green, but diopside, Heidelbergite can also be included in this list. Among the white minerals, anthophyllite, hydrated Mg silicate and common tremolite and talc, which are magnesium silicate hydrated, are product of low-grade metamorphism of siliceous dolomites and also during alteration of ultramafic rocks. Now we will come to silicates, which are common to igneous and metamorphic rocks both. Quartz as also K-feldspar including microcline and albite is the dominant plagioclase, less so anorthite. Diopside and enstatite among pyroxenes and hornblende and actinolite among amphiboles. Muscovite and biotite and to a lesser extent phlogopite among the micas are common. The list of minerals in sedimentary rock is very large, as any older rock can be either igneous or sedimentary or metamorphic origin can be subjected to the cycle of sedimentation. However, common and most abundant will belong either to the resistant group of minerals or the newly formed minerals. Among the first group is quartz, is the most common and abundant mineral. Others include minerals like zircon, garnets, rutile, magnetite, limonite, monazite and cassiterite. Precious minerals and metals like diamond, gold, platinum are also among this group. Among the newly formed minerals are calcite and dolomite. Calcite could be of mechanical, chemical or biochemical origin. Few silica minerals like chert also originate this way. Most dominant and abundant are, however, the clay minerals. The world of clay minerals is too large and complex. They are all hydrated aluminosilicates with a layered structure, very fine grained down to colloidal dimension. There are 5 major groups: kaolinites, montmorillonites, illites, vermiculite and palygorskite. Kaolinites have 2 layered structure with no replacement of Al by Si but other cations. These are formed in acid environments by alteration of alkali feldspars. Montmorillonites, also called Fuller's earth, originate by alteration of basic rocks in alkaline conditions, are 3-layered structure. Al hydroxyl unit sandwiched between Si4O10 sheets. These have swelling properties due to variable C repeat in their structure and have tremendous cation exchange property. Space will not permit to describe illites, also called hydromicas, mostly clay-sized, muscovite or mixed layers of different groups, vermiculites and palygorskite. Other clay minerals include limonite, which means either goethite or hematite, bauxite including gibbsite and bohemite, and colophon, which is sedimentary apatite, and typical evaporate minerals, namely gypsum, anhydrite, calcite and halite. Oxide and sulphide minerals rarely make up entire rocks. They occur more frequently as ore minerals under specialized geological conditions as ore minerals. However, briefly we shall consider some of them that do appear as rock forming minerals and more often as accessory minerals in silicate rocks. Among oxides, quartz is the most common as a rock forming mineral, abundant up to 12% in common rocks, especially acid igneous rocks and their metamorphic equivalents. In volcanic rocks like obsidian, pitchstone and metamorphic rock, namely quartzite, it can be up to 90%, either as quartz or as cryptocrystalline variety. Its hardness of 7, vitreous luster, conchoidal fracture and absence of cleavage are highly distinctive. It is ubiquitous, igneous, sedimentary and metamorphic rocks. All kinds of rocks are home to it. Cubic, strongly magnetic magnetite and ilmenite, both opaque and rather heavy, are routine accessories, but in basic, ultrabasic rocks may reach rock forming status. Trigonal corundum and octahedral spinel can attain the status of rock forming in selected rocks. The former with barrel shaped, pyramidal or granular form is the hardest, that is 9 hardness only after diamond, is found in alumina rich silica poor cyanides and in schists and metamorphosed impure limestone. Spinel is typically cubic, small octahedral crystals in shades of black and other dark colors, vitreous to glassy and hardness of 7.5 to 8, and gravity of 3.5 is found in ultrabasic rocks, metamorphic alumina rocks, and that are low in silica and also in marble and pegmatites. Rutile, as reddish brown black crystals, is generally an accessory in cyanides and granites and their metamorphic equivalents, as also in pegmatites. Cassiterite, though an ore, can be significant in rare pegmatites. There are other oxides like those of Mn and chromium, but they are better known as ore minerals rather than rock forming. Among sulphides, the fool's gold, pyrite, having pale brass yellow color, occurring as well developed crystals, cubic or as pyritohedron, often twinned and striated, is also massive or globular, and stalactic is the only sulphide which has wide occurrence in hydrothermal, sedimentary or metamorphic, and even is found as accessories in igneous rocks. Marcasite, which is orthorhombic, is the polymorph of pyrite known as white iron pyrites, occurs in radiating concretionary masses as sedimentary hosted deposits. Other sulphides like chalcopyrite, galena, sphalerite, and higher ores of copper including chalcocite, bornite, covellite, and ores of molybdenum like molybdenite and pyrrhotite are exclusively ore minerals and are to be found as hydrothermal, contact metasomatic or sediment hosted deposits and later enriched by supergene processes. Many other sulphides like realgar, orpiment, stibnite are low temperature derivates and never make rock forming minerals and are not considered here. We may say that rock forming minerals are those handful of minerals that are very abundant and occur in great majority of rocks that constitute the crust. Talking of igneous, metamorphic, their number at your stage will be hardly more than 8 to 12. With your increasing knowledge, you may extend them to around 30, not more. These are the minerals which will decide the bulk chemistry of the rock and its nomenclature. Plagioclases, orthoclase and microcline, quartz, pyroxenes, amphiboles, micas, clay minerals, and calcite, dolomite are the ones who attain the status of rock forming minerals. Their study and grasp is indeed the key to mineralogy and petrology. I hope you have enjoyed this lecture, and next time we might consider some other minerals. Thank you.